Every second of every day, our power grid manages a massive, continuous flow of energy. Electromotive force, or voltage, smoothly pushes electrons through transmission lines, and the physical properties of the conductor provide a natural resistance, keeping that flow orderly and contained. When we want to stop that flow, we don't try to absorb the energy. We simply break the path. We introduce an air gap so wide that the electricity cannot cross it, effectively creating infinite resistance. This schematic diagram illustrates an open circuit. As you can see, the terminals are open. The resistance, represented by R, is infinite. Because the resistance is infinite, the current, I, is exactly zero. The physical barrier holds the voltage back. But look at what happens in this short-circuited diagram. The terminals are directly connected. There is no air gap. The load is bypassed, meaning resistance drops to zero. When resistance disappears, the physical constraints that normally govern the power grid vanish with it. The system completely loses control over the energy it's carrying. This dynamic chart of Ohm's law shows exactly why that is so dangerous. Current equals voltage divided by resistance. If the resistance variable plummets to zero, the math dictates that the current will multiply at an uncontrolled exponential rate. In the real world, this math physically manifests as a fault. Whether it's a breakdown of insulation between two conductors or a line grounding out, the sudden zero resistance state pulls thousands of amps of current into a tight space, violently breaking down the surrounding materials. That localized spike in current immediately generates severe thermal damage. It rapidly melts copper, vaporizes surrounding moisture, and creates magnetic forces intense enough to literally warp heavy steel structures. Once that runaway chain reaction begins, the grid has only milliseconds to detect the fault and sever the connection before the exponential heat melts the infrastructure completely. To catch these failures fast enough, the power grid relies on a high-speed nervous system built directly into the infrastructure to monitor the flow in real time. The grid sensors are current transformers, or CTs. When a massive fault current surges through a main power line, this magnetic ring safely scales it down, inducing a proportional, readable current in a much smaller secondary wire. That safe secondary wire leads into an overcurrent relay. Inside the relay, the wire wraps around a metal core. Under normal conditions, nothing happens. But when a fault causes the current to spike, that coil generates an intense, pulsating magnetic field. That sudden surge of magnetic flux physically pulls down a metal armature, snapping it shut to complete an entirely new circuit. In a fraction of a second, the magnetic field has sensed the chaotic anomaly, closed the contact, and fired a trip command directly to the grid's heavy mechanical defenses. The trip signal travels at the speed of light to the muscle of the system, the circuit breakers. When the breaker receives that signal, a small solenoid violently unlatches an over-center knee joint. This removes the physical barrier holding back a massive pre-charged steel spring, forcing the heavy copper contacts apart with immense kinetic force. But there is a massive physics problem here. Pulling the metal contacts apart doesn't immediately stop the electricity. The thousands of amps trying to cross that newly opened gap will instantly ionize the air, creating a deadly, superheated electrical arc. This animated diagram shows how engineers solve that problem. As the contacts separate and the arc forms, the breaker blasts the gap with a non-ionized medium, like a total vacuum or sulfur hexafluoride gas. The gas instantly strips the charge from the space, suffocating the arc. This brutal, lightning-fast physical separation is the only mechanical action capable of arresting the fault's exponential heat and saving the power lines from total meltdown. Zooming back out to the macro view of the grid, that violent mechanical intervention solves the immediate thermal problem, but it leaves a network management problem in its wake. This schematic map shows how engineers divide the grid into distinct protection zones, boundaries guarded by specific relays and breakers. When a short circuit is snuffed out, only the faulted zone trips offline. The surrounding grid seamlessly routes power past it. This localized sacrifice ensures that the rest of the electrical system remains completely stable. Unaffected generators, transformers, and industrial motors continue running without experiencing massive voltage drops or severe mechanical stress. Our modern society requires massive, volatile amounts of electrical power flowing continuously beneath our feet. And that stability, is only possible because invisible, microsecond mechanical shields are constantly watching, reacting, and caging the chaos before it can escape.